Okay, a couple more things about curl, and then we'll get into divergence, the last del operator we want to talk about. So curl, we showed with the last example with the sink draining, we computed curl at different points in that field and looked at the different vectors that we had and talked about how that made the rotation. Maybe this was a really long vector and spin really fast here. So this gave an axis of rotation. Are there any points at which curl is 0? So for some vector fields, that is true. When curl is 0 at a point, we say at that point it's irrotational. So it could be that the dust particle or the particle moving through the fluid in the water of the sink is just following the flow line. It's not spinning as it goes. It's not spinning in different directions at different rates. There might be points where it's spinning and then it doesn't, and then it picks up again. So those points at which it's not spinning are irrotational points, just vocabulary for us. But what happens if you compute a vector field's curl and it's the vector 0, 0, 0? Does that ever happen? Yes, it does. In fact, here's an example. Maybe we'll use red here. Let's look at this vector field. YZ, f of x, yz, yeah. R3 vector field with components yz, xz, and xy. All right, it turns out if you were to compute the curl of this, you would get another R3 vector field. And this is the same no matter which point you're at. So maybe I should make that explicit. Curl of f at any point x, y, z is the same. It's 0, 0, 0. So it's irrotational at every point in the field. Well, what does that mean? Well, that's a special thing. If your curl is equal to 0, that means, again, you're irrotational everywhere, but another way, it means it's conservative. And we spent a lot of time trying to find those conservative vector fields. Well, this is a way to check if we now have a couple different ways of checking if a field is conservative. We had the test a couple videos earlier where we looked at the m's and the n's and did something with partials there. Well, hopefully you can see the connection with that test. It's really just another way, because when you're doing those partials, the m's and the n's, you're really doing something with curl. So when your curl is 0, your vector field is conservative and vice versa. If your vector field is conservative, the curl must be 0 at every point. It's irrotational. Therefore, there's always a potential function you could find. And so you should check that you could find the potential function for this. I think would be f of x, y, z is x times y times z. Would work. Yeah, that would do it because that would give you those partials. Again, it would be a potential function is a scalar function. When you take its partials, its gradient is a gradient vector field. Okay, so that ties up some last details about curl. And now we're going to move on to divergence. So divergence is a del operator. This time, instead of crossing, we're going to do the dot product. So we have a vector field, an R3 vector field, like the sink draining one. And so we're going to need a 3-dimensional del operator, this guy here. And so when we compute the divergence, first we'll compute it and then we'll talk about what it means. Divergence will be dotting these two vectors, the 3-dimensional del operator with the R3 vector field. This times this, plus this times this, plus this times this, where when we're saying times, we're really doing an operation. So when x looks at this, that's just a constant, so 0, plus when y looks at the second term, just a constant, so 0. And then when z looks at this, we'll go times the power down a power, so -2 times a half, so negative z. So divergence of f is actually, let me go write this, can be explicit about what we're doing here. F was a 3-dimensional vector field, and so we're now getting a scalar function. So we took an R3 vector field, we compute that divergence, and now we get a scalar function out. So it's important to note here that divergence results in a scalar function, whereas curl results in a vector field. Okay, now what does that mean? Again, you could compute divergence at many points. It asks you one in particular that they're interested in is 1, 1, 1. So the divergence of this sync draining vector field at the point 1, 1, 1 is just negative 1. Well, that's a scalar. Again, it doesn't have direction, but it has a magnitude to it. And what this is measuring now, divergence, actually how we got the word divergence, it's the tendency to leave the point you're at, to diverge from, run away from 1, 1, 1. And you could compare that to what would happen at, say, 2, 2, 2. Divergence at the point -2. Maybe more of a tendency to run away. So let's look at what happens when we use our tech tool. All right, so let's see what CalcPlot 3D can do with divergence. So divergence turns out same sync draining vector field, and we have an option to do divergence at a particular point. So you can put the flow line, again, that's your macro circulations. You can put the curl, that's your micro rotations with a direction and a rate. And then the divergence, the ability, how much do you want to run away from a particular point? You can, as usual, come up here and enter your points with your XY, pick a couple points you're interested in. We were interested in 1, 1, and 1. So it shows the point right there in blue. It's harder to see from that angle. Let's try maybe 1, 1, -1. Okay, so there we get. And then those little green vectors are, again, what the tendency to run away from that point, diverge from it. So we talked about when curl was 0, that was something important. You were irrotational. If divergence is 0, you're said to be divergence free. And you can be divergence free at particular points. It could ask you find the points at which this is divergence free. And so for a sync draining example, this is the divergence for any x, y, z. So that tells you as long as z is 0, any components where z is 0, your divergence is 0. So you're divergence free. So let's check that out. Let's try 1, 1, 0. Okay, so again, it just shows the point doesn't have any tendency to run away, as opposed to 1, let's say 1, 2, 0. Still doesn't want to run away because it's a divergence-free point. It will evaluate to 0. And again, that's as opposed to, say, this point down here, -2, has a tendency to run away, diverge from where it's at. Okay. All right, so a quick summary again of our operators, our del operator. If we have a 3-dimensional del operator, you can also have a 2-dimensional and n-dimensional, depending on what space you're working in. If we have a 3-dimensional del operator, though, there's a couple vector operations we can do. Vector operations on 3-dimensional vectors. I have 2 3-dimensional vectors, a vector field and a del operator. I can cross them, get the curl. That means a lot of different things. Microscopic rotations, rates and directions, axes of rotations. We can do a dot product of those two things, and that results in a scalar function, divergence, where it represents at a particular point the tendency for a particle starting there to just try to run away versus stay right where it's at and sort of be compressed right there. Another word for adjective for divergence free is incompressible. Compressible, yeah. And then the last del operator was one we actually had from the previous book. We know that we can take a gradient, and really what you're doing is thinking, you can think of that as a del operation on a scalar vector field. You're really scalar multiplying the del operator times the vector field. Okay.